All right, here we are in chapter 4 on exponential and logarithmic functions. Section 4.1 here is about the exponential functions. So we need to first kind of define exponential functions. So when we have different items, we have the percent change, exponential growth, and exponential decay. How do they relate? Well, percent change refers to a change based on a percent of the original amount. And it's really going to be a linear function. So it's just going to keep going up by the same amount every time, and it's not going to change. Now, once we get to the exponential growth, that refers to an increase based on a constant multiplicative rate of change over equal increments of time. So it's going to take your original amount and increase it each time. And every time we go up, it's going to start getting exponential. So we're going to go up exponentially. Now it also works exponential decay. It refers to the decrease based on a constant multiplicative rate of change over equal increments of time. And it's basically a decrease of the original amount over time. So instead of going up like this, we're going to see that one going down like that. So it's going to be a decrease over time. Now, in this case, we have the red one is y equals 2 to the x. It's exponential. And we know it's increased by the percentage over equal increments. So it's going up in equal increments every time. Now, y equals 2x is just our straight line here. And it's increased by the same amount over equal increments. Okay. So this one we had to multiply the original amount by percent. This one is just equal amount every time. So you go over one, up one, over one, up one, over one, up one. And here is an example of our increase or our growth on the red one and our decay on the green one. And really the key difference here is the value in front. And if we notice, we have a positive one here and we have a negative one here. So the negative represents decay and the positive represents growth. Okay, so these are, exponential function in the form f of x equals a times b to the x. And again, our a is the non-zero real number called our initial value. So if we had an initial value of 1, that's kind of what it would look like, and it's going to go through this point at 1. Now, if we had say we plugged in $200,000 into a savings account and it was going to grow and exponentially, then we would start way up here at 200,000 at that point for 200,000. Now, b is any positive real number such that b is not equal to 1. So if we put b is equal to 1 in here, 1 to any power is still just going to be 1. So it's going to be some factor. It might be 1.002. It might be 2.5. It could be, 22 or 20 or whatever. It doesn't matter. It could be anything as long as it's not equal to 1. Now, what's our domain? Well, if you notice, we're going way out here to negative infinity. We're going over here to positive infinity. So our domain is all real numbers. Now, depending on if we have a positive or a negative, if it's positive, we're going to only have the positive number. So it's going to be from 0 to infinity. Not going to include 0, but it's going to get close to that 0. And that's for a greater than 0, and it's going to be from 0 to negative infinity for those. And so our range, and really this should be in, it's going to be 0 to negative infinity, but it's negative infinity to 0 if you think about it. If we're going up, in this case, going that way. Okay. Now, as x goes to infinity, well, as x goes this way to infinity, what does f of x do? Well, it goes to positive infinity for a greater than 0, and so we'll see that. And as we go this way and a is negative, it's going to go to negative infinity. So we see that for that one. Now, as x goes to negative infinity, as it goes this direction, what happens? Well, they both approach 0. Now, they never touch and equal 0. They just approach 0 and get very, 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 very close, okay? So when we have a is greater than 0, f of x is always increasing from left to right. And if a is less than 0, f of x is always going to be decreasing from left to right. Now, again, like I've said, the graph of f of x will never touch our x-axis, the y equals 0, basically, because base raised to any exponent never ends in a result of 0. It gets very, very close. You might have point and 20 zeros and then a 1, but it never hits the actual 0 value. Okay, and when you have your calculator, it only goes out to 9. So it might show it's 0, but it really never touches that 0. Now that gives us the y equals 0 is going to be a horizontal asymptote. So that's going to be our horizontal asymptote. We never reach that point. And again, like we've talked about up here with the y-intercept, that is going to be our point 0a. And if it's a negative, it's going to be 0, -1. If it's positive, it's going to be 0, +1. All right, so let's look at some functions here. And what we're going to do is we're going to decide if they represent exponential functions. Well, what do we got here? Well, we got an x squared. Is that exponential? Nah, not really. What does that look like? Well, that's a quadratic. Okay, we have that x squared. So that's considered a quadratic function. Now, what about this one? We have a number raised to that value x. Well, that would be exponential. And if we think about this, our b is equal to 0.875, and we have a number out here. If we think about it, that's going to be a is equal to 1. So we just have that 1 times 0.875 to b. Now here, what do we have? Well, that kind of looks like the form mx plus b. And so that's going to be linear. Now we have another one here. This number raised to the negative 2x. Well, so instead of x, we have a negative 2x. Well, so this is going to be exponential as well. Okay, and so that's what we'd have. And of course, the way to do this would be we really would try to get into the form b to the x, and so we'd have to see what that was. Well, we'd have to take that to the negative 2, get a value, and then that would still be to the x power, and so we would do that, but we're not going to actually calculate what that is for right now. All right, so here we are going to evaluate exponential functions. So basically, all you have to do is follow order of operations, and whatever the powers show you do, that's what you're going to do. And so plugging this into our calculator, what we're going to do is we're going to plug in 3 in for x. And so if we go to our calculator, we have 8 times 1.2 to the, now that was 3 minus 5, so it's going to be to the minus 2. And I'm just going to type it in. We could go ahead, we're going to get the 5.55555, and then it rounds that last one up. We could also kind of write it as it was. It was 8 parenthesis 1.2 parenthesis to the power. And now with the TI-84 plus, and whether you have the color edition or whatever, you can say, okay, well, we'll take 3 minus 5, and as long as that stays all in the exponent, now we can say enter, and we get the same thing. So we did a little bit of work on our own here. Here we just said, okay, what is it? We just plugged it into calculators verbatim, and we got the value. So if we go back to the other one, so this one gave us f of 3 equals 5.55, and we want it to 4 decimal places, 5, 6. So that's what that would be. Now we want f of 2. So now we're going to plug in 2 into the x. So let's go ahead and do that. And again, it's just a matter of practicing putting it in. So you have to use that negative there for the 3 divided by 2. Then we're taking that times. And again, we're just going to write this one out as it shows it. And it's to the negative, and we wanted it to the x of 2. Now we have to arrow down, otherwise we're going to write stuff up here, and then it's going to give us the wrong thing. And then plus 3 divided by 2. And here we get 1 and 1/3, it looks like, basically. And so if we write that out, our f of 2 equals 1.1234. And that would be what it equals to the 4 decimal places. Again, if it told you to do it to 1 or 2 or whatever, you just follow what it says and you round it accordingly. All right, so now we have exponential growth. It's a function grows by a rate proportional to the amount present. For any real number x and any positive real numbers a and b, okay, so a and b are positive for growth, and b cannot equal 1, then the growth function has the form f of x equals a b to the x. Now, a again we talked about is the initial or starting value of the function. So, if a is 1, then our point's going to be, 0, 1. And then b is the growth factor or the growth multiplier per unit x. And so maybe we were getting interest rate and it was so many percent. So we'd put, 1.06. It was a 6% interest. It's growing by that much. And we'd take that to the x. So maybe that was our b, our a was 1. Now, one thing to note is your curves are going to look different. So if you have one, and this is say your growth rate, going up and it's exponential. Now, maybe if we had one that had a higher growth rate, it might not go up out as long. It might go up like this. But what happens is maybe at this point, all of a sudden, boom, it's going to go and it's just going to skyrocket. Okay. And I don't have these drawn very well, but what we can do is we can look at that on a graph over here on our calculator if we want. So maybe we had, maybe we're going to let a equal 1 and might have 1.2 to the x, oops, to the x for one of them. And let's say we have 1.6 to the x for our other one. So this one's a higher growth rate. And so we'll see if I have anything working. It's going to come out here and it's lower, and then all of a sudden it's going to boom, it's going to go up a lot stronger. So that's probably a much better example than I tried to draw, but that's what's going to happen is that one is going to just kind of go up slowly like that, but the other one has a higher growth rate. It's going to go boom, it's going to go up a lot faster. Okay. So the higher the growth rate, the steeper the curve's going to be. So, that first one maybe probably should have looked a little bit more like, it was higher up here, but then it kind of went like that. Whereas the other one, it went and then bang, it went up really quick. Okay. So that's how your exponential growths are going to look. And same would be for a decay, except you're going to be down in the negatives and it's going to look the other direction. All right, so here we have the population of China was about 1.39 billion in the year 2013, with an annual population growth of about 0.6%. This situation is represented by the growth function pt equals 139 times 1.006 to the t, where t is the number of years since 2013. So that means that this was our t0, and this was going to be basically our a. Okay. And if we think about that as our A, well, that's what we have here, A. And our B, well, how did we get B? Well, we converted this to a decimal, 0.6% to a decimal, 0.006, and it's growing by that. So we have our initial amount, 1, plus that, and so it's going to be 1.006. And then we raise it to t to whatever number it is after that. So what happens is, now they're saying, well, to the nearest thousandth, what will be the population of China in the year 2031? Well, let's see. How many is that? That's going to be t equals 18. So we want p of 18 is equal to 1.39 times 1.006 to the 18. So we're going to use our calculator once again. Now let's clear out of here. And so we're taking out 1.39, and we're going to take that times 1.006 to the 18 and bring our thing down in parentheses. And so it says 1.548026722. It said to the nearest thousandth, so we just want 1.548. And so that's going to be 1.548, and it's billion people. So putting our correct units on here is going to be key. It's 1.548 billion people, and we can even put a little bit more in 2031. So that would be how many people are going to be in 2031. All right, let's pause there and we'll come back for more.